special class is that it sort of contains almost anything. It's a bit of a broad title, and I'm probably not going to, n's not going to be that big in this one.
It's hard to hear you when you move here.
Oh, sorry.
Maybe it's...
Is that okay?
Yes, it's better.
All right, forgot to turn it on. This is work my main field really deals with functional differential equations and things, but occasionally we have some problems that deal with conservation laws, and I kind of got into it from the back door on a visit to Vancouver with George Blumen, who introduced me to Noether's theorem and some other results. And I had two colleagues in New Zealand who were quite interested in this sort of stuff as well. Unfortunately, the person I relied a lot on, Marika, she passed away last year while I was in Korea. And I worked quite a lot with her doing, well, she was doing a lot of the computer work. And I find that I'm now doing a lot of stuff by hand until I can learn computers a little bit better. So anyway, conservation laws for a special class of these equations. Well, let's just maybe review just briefly what we're on about with conservation laws. We've got a differential equation of some sort, and we're looking for this type of a relationship here, a perfect divergence. Now, the nice thing that connects this, of course, is that there has to be another operator out there, Q, the characteristic. It's a biconditional. If it has, everything here is smooth, but if it has a conservation law, then there's some Q out there that'll do that. And that's called a characteristic. Of course, if Q is 0 and H is 0, then we're not really any further ahead. It's a trivial characteristic. If Q is 1, for example, then the PD is in divergence form. Okay, one of the few tools that we have around is Noether's theorem. Now, I guess most of us have seen this at one time or another. Just X and T space here. This is just notation. The idea is that if there's some variational background to the problem, that is, if H is an Euler-Lagrange equation. So this E here, this Euler operator, is this complicated thing, depending on how high the derivatives are in L. They introduced this Lie characteristic. Now, this Lie characteristic turns out is the same, one and the same with the characteristics that I just talked about. The hard part is finding it. And this is where Noether's theorem comes in. But there's no such thing as a free lunch. With Noether's theorem anyway, you have to deal with things like these prolongations of the vector. Let me just back up so that I put that one in. Well, this is the kind of a Lie-Backlund transformation here. You deal with these prolongations here. So these phi's, for example, are in terms of the characteristic, and these xi functions. You then have, what's the next ingredient? You have this Noether operator. Okay, notice there's a characteristic in there as well. Here, I tend to think of this thing here is the same as the Euler operator, except you're using the, well, E of I here is just the Euler operator, but you're using the first, well, the ith derivative, or ui instead of u. So it's using ux instead of u in the Euler equation. And the crunch with this one, the place where it all comes together is down here in this operator identity, Noether operator identity. And what happens, this is in the classical stuff, I'll take you through this briefly, but well, here's the idea. If you can find something such that that's an identity, okay, now the things that you don't know are the xi, you've got xi's, etas, and things there, then you can find that divergence, and your Q here is the characteristic. That's very, very short version of notice there. It's quite complicated, actually, in its mechanics. The thing is, though, if we start this whole thing off, what drives the thing? The first assumption is that I can write it as an Euler-Lagrange equation. Right? And that's a lot of equations we're interested in. You can't. So what can we do about this? Now, there are lots of things. This is a huge field, and there are a lot of people working on it, making all sorts of progress and doing all sorts of things about it. One of the ideas that recently came up, though, was this idea of what they call using a partial Lagrangian. And it's one of these ideas, once you see, you say, oh, yeah, why not? Let's try this. So if the thing isn't a Euler-Lagrange equation, so let's suppose it isn't. In 2005, people were doing this in kind of a haphazard way, but they formalized this idea of this partial Lagrangian, and literally what they're doing is you can carve off a Lagrangian part of the equation, this thing here, and then you've got some other thing over here that isn't an Euler-Lagrange equation. Okay, we're getting into more dangerous ground. We've just left the comfortable world of the calculus of variations and everything, and all comforting things like Lie algebras and everything that we might have with Noether's theorem. Just throwing that out the window. But we're looking at it in a pragmatic way. Okay, suppose we do this. Can we make this work? Can we nonetheless pull this one off? And the answer, well, what you do is you define this, what they call a Noether type symmetry. Now, the idea behind this symmetry is you go hunting, basically, for a function b here, and you have this type of identity. You can find a b such that you can get away with this. You're actually worried about finding a characteristic for that f. So if you could do this, then we'll see in a minute you can get a conservation law. And I haven't gone down and read all the proofs of everything about this, but it is covered in the reference I have in here. They kind of formalized what a lot of us were trying to do over the years. So this is kind of the important relationship here. And what happens? Well, suppose I could do that. Suppose there is a b. There's no guarantee here, okay? There's no guarantee, of course. This is always true anyway. This is Noether's identity. And if I'm thinking about it here purely in terms of that Lagrangian, that's fine. I'm still on safe ground with that. But it's EL, it's not the PDE I'm after. But if I could do this, then if you remember that the thing I'm after is equal to EL minus FG, then just a simple calculation tells me that I'll have the divergence of this. So it's got this B in it now. Otherwise, it's the same as the Noether's theorem. So this is the idea of these partial Lagranges. Can we get away with this sort of a thing? Okay, well, let's have a look. So this is the simplest example I can think of. It's a heat equation. And we've got a lot of very complicated equations, but this is just to give you an idea of maybe some of the mechanics here. Okay, so heat equation. Well, I can carve off this bit of a Lagrangian. Okay, the U of t is the problem. Okay, but this is what it would be in that formulation. Okay, I've got an L that's got a first derivative in it, so my prolongation has to go out to U, d by dux. Okay, so I've got this prolongation operator here. This Q down here I'd actually put into there, and I'd come up with this long equation here, and then I would try to figure out the coefficients of the infinitesimal generator. That is, figure out the tau and the eta xi. All right, so simple example. Okay, and this is, I'm not going to drag you through another one of these, okay? This is just to give you an idea of kind of what's going on. It's the simplest one I can find. You get these sort of relationships, lots of little differential equations. So this is very much like the ordinary symmetries and so on, differential equations. You get lots of little ones down here. You get some involved in this b. You don't know what b's you're hunting for. You see, this is the price you pay for leaving the Lagrangian world. Okay, and if you carry out through that, you can get this sort of a non-trivial solution. And it's this eta here is a function of t and x, and it's sort of an adjoint heat type equation. And I mean, again, this is a simple example. It's really well known that the heat equation has any number of conservation laws in there. But this just shows it very clearly. Any solution, any eta you find that does this will give you a conservation law, and so you can use whatever heat polynomials, whatever you want to get that. So that's a very simple example. Now, I noticed that somebody else did this nonlinear sort of a wave equation. I'm not going to go through all the equations of that one. But sometimes it gives you something that isn't quite so obvious. And in this case, if you go through that same sort of procedure, there's your Lagrangian. Okay? It's pretty robust. You can nibble away a Lagrangian one way or the other, or however. Okay? So you don't have to have a special Lagrangian in there. Although strategically, you want something that's going to actually take out highest derivatives or whatever. Anyway, so you go through that kind of a process. You do get this x, this Lee-Backlund function here. These are your b's. Okay, so we've solved all those differential equations. Now, what is it telling us? Well, if you set c1 to 0, or c2 to 0, c1 to 1, or vice versa, you got a two-parameter family here. The first one is obvious, and you feel like you've wasted a lot of time saying the obvious. It is obviously a divergence relation, so there should be q as a constant in there. Q equals t is a little bit more interesting in this one because you have, it's not, well, to me anyway, it's not totally obvious that t is a characteristic for that equation since there's no explicit t dependence or anything in there. Nonetheless, it's there. So, not quite sure what to make of that type of conservation law for the nonlinear wave equation. Maybe telling us something. Well, I thought, okay, if we've got this great system, let's take it for a real test drive. And I must admit, I did punishing, really, to try this one. I said, let's try it on the fifth order KdV equation, okay? So this is a KdV equation, and we're going to hear more about that later. But I just put some constants in, the alpha, beta, gamma, constants in there. And it's kind of written this way because it captures a couple of equations that I know about. I'm sure there are plenty of other ones. The ones that came up from Lax in the KdV hierarchy. The one that Ito produced, the Cooper-Schmidt equation. Now this one, I have a question for the audience. I've seen the spelling of Cooper-Schmidt 3 different ways, and I can't quite figure out which is the right one. Every time I give one of these sort of things, people say, oh, no, it's got a C in there. It's not just a Schmidt. And then other people correct me and say, no, there's no C in there. Everybody makes that mistake. So I don't know. Anyway, fifth order KdV, all right. We do the standard thing of let u equal Vx in there. Okay, you get this equation. Now, why do I want to do that? Because I want an even derivative in here, and I want to carve off the highest derivatives from Lagrangian. That's what I'm doing. So I take that, move to the next one. We can use this Lagrangian. Now, I must admit, I speak glibly of this. It actually takes a while to kind of nibble away and come up with these Lagrangians. It's kind of like solving an inverse problem, but if you get it, you're in great shape. Now, this one's really interesting if you decompose it like this, because the alpha minus beta case is instantly important. You can see immediately why that's a critical case. Because if alpha is equal to beta, then in fact, it's an Euler-Lagrange equation. So there's obviously something happening with that. Now, okay, that's all really neat. Lax and the Ito ones are Lagrangian. The Cooper-Schmidt, with or without the C, is not. Okay, well, I took it for a test drive and did lots of algebra because, as I said, my colleague that I worked with passed away, so I was doing it by hand. There's 22 small little differential equations that you juggle. And I was a bit hosed off, to tell you the truth, because the only non-trivial solutions I could get was when it was Lagrangian. I was rather hoping maybe something else might come up, but no, it doesn't. It's in the Lagrangian case. You get these these characteristics. I call them P1 and P2 because they're actually characteristics for the M equation that I differentiated. And in the end, well, one of them, this one here is just xi times u. But the other one gives me this non-local symmetry, which I'm not an expert at all in non-local symmetry type stuff. I kind of view it as cheating the problem if you have to put an integral in there. But there are people that do certainly use that. Okay, so that's taking the KdV out. Now, this technique has been applied to some other equations. Particularly now they're going after higher order equations. They're looking for higher order characteristics. That is, characteristics that contain second and third derivatives for various reasons. And the reason I've gone through this one here was a warm-up to finding higher order characteristics. But this kind of put me off a little bit. I don't, call me lazy, but I thought I'd maybe look at this a different way. And so I asked myself, well, is there some easier way of doing this? Or at least trying to get somewhere with these sort of problems. Okay, so Noether's theorem is, how do you describe it? It's seductive because it gives you this sort of a systematic way, provided you're patient enough to do everything, to find these symmetries if they exist. We're out of the comfortable Lagrangian world here, so it may not pick up all of the conservation laws, so there are some problems there. But nonetheless, okay, we'll move on. Well, here's a simple-minded approach, and sometimes you can get somewhere with this. I go back to this here. That's my conservation law. This should be brackets here. It's an operator, the Euler operator E. And remember, the divergences are the kernel of the Euler operator. So if the Euler operator is 0, then I've got a divergence. And this has to be an identity, of course, for all functions, also U, smooth functions. All right, well, this is by no means a new idea. I know it goes back to the 60s and the direct methods and things, and more recently when I was in Vancouver, that's not that recent I realize, but when I was in Vancouver, they were exploring how you might be able to effectively use this type of technique. So I'll just take you through some real simple examples. Sometimes you can find some qualitative information out. Okay, so the idea is trying to discover whether something has a conservation law. Okay, well, here's a simple example. This is one that I kind of got from Marshall here. This one. So this is just a simple example of what might be done with something like this. You start with this, and then we generally move to this maybe, and then we complain that we've lost a conservation law. Right? We've lost the arbitrary function of u that you can put in front of there as your conservation law. Okay. Now, this kind of begs a natural question. This is not the mind of an applied mathematician working here, but this is the mind of just somebody in mathematical curiosity. What can you put there? Is there anything you can put there that'll give you another conservation law? If I let you do anything you want here, can you get a conservation law? Now, when I looked at something like this, I thought, that's pretty broad. I probably should be able to do something. So you go at it like this. You just say, okay, well, the Euler operator has to be 0. And so you get these sort of expressions. That's just expanding it out as an Euler operator. But it has to be 0 identically for all functions u. Okay, so you get some equations like this. Again, this is a simple example. But the thing is that it socks it down right away with this ux squared. That has to be in there. And I didn't expect it to be quite so tight that that's it. Okay? Now, that's just, what I've done here is, I'll back up for a moment. I put a q in here. I'm thinking of q as some function of u alone, okay? And I stuck it into here, I get this sort of an equation out, and this is what it tells me B has to be, and it's clear you can get this kind of a divergence, well, derivative term. Here A is just integral of the beta arbitrary function here. These arbitrary functions come up from integrating these simple relationships up here. You might ask, yes, okay, well maybe you can do that. Great. You got that conservation law. But you just lost the divergence I had. I'm greedy. I want two conservation laws here. Can I design this thing to give me two, both divergence and a function q of u that's not a constant? And the answer is yes, of course. These things, you get the same equations if you go down here. It's the same thing. And you wind up with this equation. Here A and B are constants. This has these two characteristics. Well, I mean, Q, one of them is a special case of the other, but the point is that it has two conservation laws. The other point is it's quite tight. There aren't any other functions that have that property except this one. And in particular, this ux squared has to be in there. So the simple sort of an approach tells me some structural information about what has to be present if you're going to add a second derivative in there to have two conservation laws, one of which is the non-constant, the non-constant characteristic. So anyway, it's a simple problem, but it's illuminating that it comes so quickly and that it's so tight. Okay, well, let's go on to something else now. And now for something completely different. It wouldn't be a conference on conservation laws without somebody mentioning the KDV. We're going to hear more about that anyway in the next lecture. But here's a wonderful property of this is third order KDV in divergence form. A wonderful property of it. It's all well known, old as the hills. But it's worth saying here is that the KDV equation has this term here is actually a characteristic for the conservation law. It concerns what is a Hamiltonian density, as they call it. Really attractive properties, what motivates, I think, some of the KDV hierarchy. And using this kind of a simple approach, I asked, well, what other equations have that property? What's special about that? Is there any way we can kind of see what the underlying structure of that is outside of the KDV thing? What I'm thinking of here is that if you take, I lost count of how many modified KDV equations, general, modified, form. But here's the question. If we change this thing around, do we still get this nice relationship? How much can we tweak the KDV equation and still get at least this much? Now, I'm not going to talk about things like infinite number of constants of motion and that stuff, but all I'm asking is three conservation laws. Okay, well, maybe we can do something with that. Let's just look at this. This is the general form. U of t plus stuff that depends only on derivatives of u. So u1 is ux and un is uxxx n times. Now the problem's particularly tractable because if I take the Euler operator of that, well, q times qx here, this is the derivative of q, that's a perfect differential, isn't it? And the Euler operator vanishes for those. So that conveniently goes away. And I'm left with just looking at this. Okay, now this is getting some of the nib of evolution equations. Because this, really when I answer when is that a characteristic for Q, then I'll kind of have it for any evolutionary equation that it's this U of t that's causing things to get tight. Okay, anyway, so I went through this, okay, and remarking earlier, I'm sure there's a lot more clever way of doing this or seeing this, but on my part, I don't have two proofs at the moment, so I thought I'd at least explain a little bit. Okay, you go through this, it's ugly.
Any counterexamples?
What's that?
Any counterexamples?
I hope not. But it makes sense when you see the evidence, it certainly makes sense. This is just, okay, just algebraic grunt through that. And the idea is it has to be true for all possible u. And if you collect coefficients, you get this sort of a term here, and you get this w function here, and those all have to vanish. Now you can lose heart at this if you've done Noether's theorem on the fifth order KdV, and you start seeing this stuff again, and then you start losing heart. But in fact, and I asked down here, is it tractable? In fact, it is. I think I'm slow off the mark. Because if we return back to the fresh A derivative, the fresh A derivative is kind of like a chain rule for the Euler operator. The adjoint is. We look at the fresh A derivative, and its adjoint here. The Euler operator, this is, as I said, sort of like a chain rule there. Yes, it's ugly. But this is what you get. You get the self-adjointness of the fresh A derivative. That has to be, in order for that Q to be a conservation law characteristic, it has to be, it has to produce a self-adjoint fresh A derivative. This is what I'm saying. There must be a much more elegant way of getting this. But at the moment I don't have it. But once you see that, you say, okay, we've got the Helmholtz conditions. Right? Yeah, I don't know if people remember much about that, but we've got these Helmholtz conditions for something to be an Euler-Lagrange equation. It's exactly the self-adjointness of the fresh A derivative. So it's obvious kind of in one direction if you have an Euler-Lagrange equation, because H doesn't depend on T, that U of T is a characteristic for it. But maybe not the other way. But it's the only possibility. But that's what it comes out. It has to be Euler-Lagrange. Now this, I think, I kind of pasted this from a paper I wrote earlier, and I realized that in fact there's a much simpler way of seeing this. Okay, if I think it's one of these cases where if you had because I had the fresh A derivative on the table, I just used it and it was an easy calculation. But in fact, what's going on with this other calculation is very simple. We all know just from 1D, if I have some variational problem where, let's just make this x, y. If I have something that just depends on, x and, y and y prime, then we already know we've got a Hamiltonian. So we already know that this sort of a thing is going to be constant. And if you actually remember the proof of that, you get this times your Euler-Lagrange equation. Okay, so in fact the characteristic of the derivative is the derivative for that. Now this is just in 1D, but the similar result holds in 2. You get a perfect derivative. Now you might say, well, that's not quite what I was looking for, but yeah, it really is, because I'm in this situation where I've got that, but of course, and this is exactly what the first line of that does. I get this sort of a derivative relationship here. And because I know that this is a perfect derivative, that's what that long fresh A derivative calculation was, that's obviously going to be 1. I guess I'm using x instead of t here, but it forces this to be 1 as well. So it's just a chain rule. That's all that really comes down to. It's like the most elementary one. But anyway, we can make it look good with all the fresh A derivatives in there. So the type of equations that mimic the KdV are like this, in the sense that they have these three conservation laws. They're this sort of form here: ut plus some Euler-Lagrange equation differentiated by x equals 0. And these things, yeah, from the construction that we've done here, we're always guaranteed three conservation laws. We already have divergence in this form. U is going to be a characteristic for a conservation law, and the Euler-Lagrange equation itself is going to be one. And so this is one way we can access higher characteristics that have higher order derivatives. Very special class, but very pretty sort of a relationship you can get with these. Now, the thing is that this calculation isn't completely wasted here. I mean, this is very interesting. But it also, really, if you think about it, it was the characteristic acting on this that caused all the problem. That's where the heartache comes from. That requires a lot of structure to get a conservation law characteristic that wants to play with U of t. Okay, it has to be in Euler-Lagrange. Okay. So this part really wasn't that important. It was really what was happening in here. So we ask about, well, let's go, you always have to go through the rogues gallery of some equations here. The third order equations, the KdV we've seen does that. What other equations? How can you tweak the KdV equation and still get this sort of stuff? Well, really all you need is an Euler operator here. So if you've got, well, that would be be linear in U2, and then A and B would be functions of U and first derivative. All you really need is that. So any KdV type equation, anytime you have this combination in there, take the Euler-Lagrange equation of it, you'll have the characteristics. You'll have second order characteristics. So that's the way of accessing it. And then you can see immediately why things like this is the MKdV equation. That obviously is going to, of that form. It certainly meets that sort of a condition. But other ones like the deformed KdV and the KdVB equation aren't going to work. They don't have that property. They're different. KdVB actually is, all right, it does work if mu is 0, but then you sort of lose the b out of it, don't you, when you do that? So it's not really, we don't really count that. What about fifth order equations? Well, things, we don't want to do inverse finding too many Lagranges for fifth order stuff. But for fifth order equations, well, if I've got something in this form, this is a particularly simple form, then it immediately kind of reduces into this type of form. And it happens that a lot of equations are like that. So we've already looked a little bit at this fifth order KdV equation. And that certainly, that's the construction, I believe. I'm not an expert on how they construct the hierarchy of the KdV, but I believe that's a crucial quality, that it has to have that characteristic that preserves the Hamiltonian density H here. I believe that's how they're constructed. So there's no surprise that this one, the lax one, has that property. Poor old Cooper, I didn't spell it differently anyway, Cooper-Schmidt equation, well, it's kind of, comes close, so to speak, in the sense that it's not wildly out. Most of the time, the other fifth order equations that I've looked at, and there aren't that many but at any rate, most of them don't even come close to satisfying. And yet, if you wanted to, I mean, we're not in the business of just creating equations to play with, but if one wanted to, one could create quite easily fifth order equations that have that property. Just choose any H and run it through. So there's a lot of them around. It's just that we're not bumping into them so much, except for KdV. There was one here that I was brought to my attention by my colleague had mentioned earlier, that she had looked at And then it was looked at by this tan. And here, we maybe go back to our idea, can we tweak the, how much can we tweak the KDV equation and still keep those nice properties? Well, Tan looked at something, hang on, got that right? Yeah. Tan looked at something like that. Now, this n of u here is something of this form here. And was, I guess the question I have is, well, is that going to be in the category? If I just have an n of u in there of this form, is it going to give me that? And in fact, it does in here. He was looking at it, I think, in embedded solitons sort of thing. And he was looking for cases where he got it. And this was exactly one of the cases. And it might be the only case where it works. But if you can pull that off, then you've got, I mean, there's your conserved Hamiltonian down there. So that's just some ways that you can use this. You can use this stuff. Now here's another one that you can think about for a minute. Here's a I don't really want to get into get into too many designer equations. Okay, we've got enough equations to play with. So, but we might ask some questions here. Very similar to the one, that simple example. And I don't want to go any higher than that because it's Friday afternoon, and for no other reason. We don't want to see too much. But here's a question here. Suppose I have some function h that, say, depends on u and u1. And we've learned that odd-order equations like conservation laws like Q of u, odd-order equations like those, all those KDV ones that we looked at like u, first-order one really likes having functions of u, third-order ones, but second-orders don't. They don't like to play with that. So suppose that I have an h like this, and I ask the question, well, essentially what h's give me conservation laws. Now, we mostly answered this earlier, but let's just think about it for another minute. U of t, and then, unlike the simple example, I'll force that to be an order of Lagrange equation. I won't even ask it to do the divergence now for the moment. Now, we've already seen one sort of like this. But if we ask this question, what happens in this case? Well, this is the problem. If I've got some characteristic out here, and I'm asking this to be identically some divergence, we've seen that Q itself has to be the Euler-Lagrange equation of something. Now the only option, I'm not wanting to look for high-order characteristics here. I don't want a characteristic that's actually an operator of higher degree than my original equation. That's not going to help me much. Although that's an interesting point. I'll point out that the relationship is totally symmetric. They share. If one's a conservation law characteristic, Q is a conservation law characteristic for H. H is a conservation law characteristic for Q. So there's that nice symmetry in this direct approach. Anyway, for this one, well, it brings me back to this Q of U. It's the only one that's going to be an Euler operator, a bit degenerate, but it's the only one that would work. And, okay, well, I can play plug it in. I won't bother with all the algebra. I think it'll end early, but what's the upshot of something like that? Again, these are just simple kind of toy problems. Well, the upshot of this one is that if you play this game again, if I call this thing H again, if you play this game again and go through some of the equations, I'm overusing H here, let's call it F. This forces it to be Euler-Lagrange of some sort, and what you get in the end, I suppose, is that this thing, this is where they get kind of, I don't know, kind of funky when these are just, that's an arbitrary function of u. Okay, well, no surprise, that's just a differential there. K is some constant, and then if I want, I can add a constant in there, but these things aren't really that important in that. E of those things is going to be 0. That has to be true. Now, what happens with this is I get right back to my earlier equation, but it has maybe a little bit difference because I assumed everything was multiplied by the second derivative, but I get back to the same type of equation with this funny logarithmic Hamiltonian being consumed. So I end up with just a cut to the chase here. I think I wind up with the type of equation where, once again, I have no choice. I have this type of structure. There's no choice about it. That has to be present in my second derivative. So it begs a question that well, obviously this is very tight. This is a special equation, and I'm in a whole room full of people that do applied maths. And this is really simple. I mean, you can do this. Probably already did it while you're waiting here. But this type of thing here, when you add this onto one of those ut plus f of u ux, this is obviously a very special equation. It's the only one that does this. So, I'm open to ideas if anyone's really seen this one before. I don't think there's anything new here. I think people must have bumped into this many times over. But in this very simple, direct framework, we get it.
There is a guy called Philip Resonal. He produces such equations every day. He likes to split them,
Yeah.
like a machine, like some machine gun. Go to the net and look for his name, and then you will find
He probably has come up with this one. See, I'm very conscious. I don't want to start inventing.
variance of it, or variance of the variance of it. Every other day he has equation with that.
Yeah, this is what I always have the fear of, that I'm going to have this, I don't want to spin off equations just to spin them off. I just find that one's, because it's in such a simple framework.
I mean, look, Philip Resonal.
Okay. Maybe we'll...
He's our friend.
Okay, well, anyway, that's very simple. Like, we can, my goal here, the things I was trying to do, and I don't want to get too far into notice there and all of that, is to look for higher order characteristics. And any way I can find, okay, I've tried notice theorem, and I'm sure that works if you've got the fortitude to carry out the calculations, or can find a good student who knows how to use a computer really well, because I've got these least symmetry and all these other packages. But it's brute force. It's kind of using, it's a beautiful result, but it's using kind of like using a meat axe instead of a scalpel. You end up in this mode where you're just grinding through thousands of equations and coming up with, like the KDB, coming up with something that you could have gotten much cheaper some other way. And so I was rather hoping that something like this, where we can at least identify certain structures, would be of use later on for identifying some conservation laws. So looking, instead of its specific equations, trying to find structure in equations that we know admit some conservation laws. So leave it at that. Marshall, thank you.